In this video, we're going to look at a simple numerical differentiation technique. So we're going to start off with a function, and this function here is y is equal to x squared. Now we're going to look at the gradient of this function at a point given by x is equal to 1. So you can see here that we can move this white line round about the function, and as we move it round about, you can see here that the value for the gradient changes. So here in this instance, at the point 1, you can see that the gradient is a value of 2. Now we want to be able to generate this value for the gradient numerically. So we're going to first look at it in terms of something called a forward difference. So I've drawn out here the forward difference. So let me zoom in on this. So what we're going to do is we're going to take the point 1 and we're going to add on a small difference here. Now in this instance here, we're going to add on the value of 0.1. And then we're going to find the value of the function at that point. So we look at the value of the function at 1.1. So at 1.1, the value of the function is the point here where it crosses the line, 1.21. So you can see here that the value for this gradient isn't exact. In this instance, the forward difference gradient gives us the value of 2.1. But we know the actual gradient is a value of 2. And we can see here the error that occurs, because the actual gradient here is in white and it's a little bit less than the gradient we've got here for our forward difference because of this little difference in height here. But it's not too bad an approximation. Now we can move on to the second approximation, and this is going to be called our backward difference. So again, we take the point 1, but in this instance we subtract off a small difference. In this instance we subtract off the value of 0.1. So instead of having the point 1 here, we've got the point 0.9. And we again go on to the function and find the actual value at that point. And this is the value here. So you can see here that the gradient for this backward difference again is not the same as the actual gradient of the point. And if we have a look here, we'll see the actual values. So for the backwards difference we get 1.9, for the forward difference we get 2.1. Now finally we can look at generating both a forward and backward difference. So if I was to join both of these points together, so that's this point here and this point here, and you can see it's joined together with this little pink line, then what we'll have done is we will have generated the value for a forward difference of 0.1 and a backward difference of 0.1, and then we take the actual value for the gradient to be the gradient of the line which joins these 2 points, and that is called our central difference. Now you can see here in this instance that the central difference is actually a value of 2, so it is worked out and given us an exact value for the gradient, and it is equal to the actual gradient. Now this is actually going to work exactly in all instances with this particular curve, because this particular curve is y is equal to x squared, and because of the symmetry and the geometry of this, we're always going to get an exact value. So let's just move this down, up and down a line, and you can see that the value here is for the central difference and the actual gradient is exactly the same. Now that's not always the case. If we were to put in a function, for example, instead of having a function x squared. If we have a function x cubed, then we wouldn't get an exact value for this. But we're going to use this particular example with a value of 1 in order to generate our little algorithm. Now the actual algorithm is very simple, and we've got it written out here. So in order to find the derivative of a point x, then we use our f of x plus h, which is the forward difference, and then we take away f of x minus h, which is the backwards difference. So in effect what we're doing is we're looking at the height here from this point here in the pink line to this point here in the pink line. So we're looking at the gradient in effect of this pink line. So the f of x plus h minus f of x minus h gives us the height of that pink line. And then we're going to have to divide it by the distance. So the distance in this instance is the h here for the forward difference and the h for the backwards difference. So that's a value of 2h. So this is the little algorithm that we're going to use. And of course, we can use different values for h, and the smaller the value for h, the more accurate your result is going to be. Now we're going to use a value of 0.1 for our h. So let's go ahead and we will code this algorithm in our assembly language. Here is our algorithm written in our assembly language. We generate f of x plus h here, f of x minus h here, and then we generate the f of x plus h minus f of x minus h upon 2h here. And finally, we pop the answer into register R0 and store it in a memory location called answer. So you can see here we have our variables. We've got the value for our x, which is the point at which we want to work out the derivative. So we're looking to find out the rate of change of the function f of x is equal to x squared at the point where x is equal to 1, and the value we should be getting is an answer of 2. Now the value for h we said is going to be 0.1, and then we're going to have the value for our ax to the power of n. So in this instance what we're going to do is we'll put the value for a is 1, okay, and the value for n is 2. So that's simply going to be ax to the power of 2, and a is 1, so it's simply x squared. And then we're going to store the resultant answer. So let's load this into the machine and we will see it running. I have loaded the program into the ROM, so let's run the simulation. So that's it running now, and you can see the ROM and the RAM being accessed, and we have our controller here as well, pulsing away with all the sets and enables. So let me fast forward this and I will get to the final result. Now that's the simulation finished, and you can see that the final answer is a value of 2, which is in register R0. We can also drop into the RAM and you can see that the answer 2 is placed in this memory location. So we can generate a numerical differentiation using a simple central difference method. And I have tested this out in several other polynomial functions, and it has worked very well. So thank you for listening. I'll get you on the next video. Goodbye.